I mean, like, isn't that everywhere? Okay. Morning, everyone. See, okay, the speaker today is Alvaro and tell us about thermalization and thermodynamics of many body systems. So about many body systems, and then later more general results about thermalization. He put some lecture notes on Discord, and are they on the website as well? If they're not yet, they'll be very soon. So if you're watching from home, you can follow along the lecture.
The lectures I wrote have more than I'm going to say in these couple hours. And yeah, thanks, Lydia, for the introduction and for setting this up. Okay, so I guess what I'm going to talk about is a bit of a different topic than the rest of the lectures. And to say that maybe the motivation of it is a bit different, and it's also maybe a bit more mundane. The motivation really is that, we have and one of the interesting things about quantum physics happens when you do together, many small particles together, because we expect that somehow interesting things can happen there, interesting physics. And the challenge, of course, of this field is that if you want to understand the systems, the most naive thing you can do is you have your matrix, which is basically which describes your state. And this matrix has a dimension which is huge. It's basically exponential with the number of particles, like 2 to the n, something like this. So basically, if you try to do this in practice in a computer, you can only reach very small system sizes. That sometimes they don't even converge to the thermodynamic length. So the hope basically is that by understanding the physics a bit better of the systems, we can circumvent this problem of having to diagonalize these matrices, and we maybe have new methods, either analytical, numerical, or a combination of both. So what I'm going to talk about is basically it's along these lines. This is a very general topic. What I'm going to talk about is, as you see here, it's about the thermal states of these many body systems. And just the very general definition is just this. So we have the state rho, which has this huge form. So everything I'm going to say in the next 2 hours is about this state, no other state. And the particularities of this is that it's basically the Hamiltonian. Hamiltonian is a local Hamiltonian. And essentially what this means is that the Hilbert space is composed of many particles, and this operator is such that it's a sum of smaller operators. And with smaller, I mean that each of these terms, there's many of them, has support on only a small number of particles. You can imagine, for instance, we can arrange, like in a cold atom experiment or other kind of experiment, a chain of atoms, you arrange them on a line. We usually interact is by acting, basically with the nearest neighbors. This one will interact with this one and this one. So it's described by a Hamiltonian like this. So I guess the idea is this type of Hamiltonian is ubiquitous. The interactions between many particles end up being local, just for very obvious reasons. And of course, the thermal state is one of the most interesting states in which this type of system appears. And there's many reasons for it. I mean, first of all, of course, we know that thermal states are everywhere. Usually the systems are going to be coupled to some external radiation or something like this. So they're going to end up in a thermal state of some temperature. Another way in which they appear is actually, we'll see this in the last lecture a little bit. That if the system is isolated, following under the dynamics with this Hamiltonian, it can be the case that it ends up in a state that looks like this. So somehow the system, since it's very large, it can act as its own God. And I mean, and there's many other reasons why these states are interesting. So I mean, there's from the point of view of condensed matter, material science, quantum chemistry, and so on, we understand many properties of thermal states. For instance, I don't know, the fluctuation dissipation theorems, linear response, the transport that appears in this type of system, and so on. The non-equilibrium dynamics out of equilibrium of the thermal state. And there's also interesting phase transitions you can study. And also, another thing, and one of the reasons I'm interested in states is because they're important for computation. So the thermal states, even just for classical systems, they're actually quite a natural data structure, and they appear, for instance, in machine learning. Even the case that in quantum algorithms, algorithms will be a subroutine in thermal state. And it's also known, for instance, that when you go to these many body systems, when you go to very low temperatures, it may be the case that they actually encode the solution of computationally hard problems. No? So I guess another motivation of this is that actually studying the complexity of thermal states is a fundamental problem from both the physics and the computer science perspective. No, there's somehow an interplay between these things. No, it's really interesting nowadays. No, because I mean, we're now in the age where people can actually prepare these systems in the lab. No, strongly coupled many-body systems. No, so you have all these experiments with like cold atoms, ion traps, all these different platforms. No, probably you've been hearing about this. No, there's all this quantum computing hype going on. No. And so this really motivates the study of strongly coupled many-body systems, no? And of course, in the context of this school, well, this is also quantum thermodynamics, no? So one hope I have with these lectures is that somehow you end up with some. I mean, what I'm going to say is it's not very thorough, no, it's very shallow results, let's say, but hopefully this what I'm going to say tells you that maybe you can, in your quantum thermodynamics problems, whichever they are, you actually have tools, analytical or numerical, to study quantum thermodynamics of these spin systems, no? Because maybe usually in many problems you study maybe more like fundamental frameworks, like this research theory framework, no? Or maybe other types of systems like open systems or spin boson model, this type of thing, no? But I think there's also tools to study spin systems, no? Which they can be complicated, but sometimes they're not. No? Okay, so that's the introduction. Any questions? Great. Okay, so actually, of course, there's many things I could say about these thermal states, but I'm going to focus on two, which hopefully are like interesting enough. So one of them is the correlations. So correlations that appear between different parts of the system. No, of course, there's a very clear notion of what it means to be a subsystem here. No, that's geometric locality. No? So I just want to see how the correlations appear in this type of state. And the second one is about subsystems. So single subsystems, no? So I'm going to tell you some mathematical results about the following. So I can separate my system into A and B. I'm going to tell you some results about the following state. Maya on A, basically. Okay. But actually, first of all, I actually need to introduce a couple of mathematical terms, not too complicated. Some definitions. First is the operator norm. So I have an operator A that lives in my Hilbert space, and the operator norm is basically the following. I mean, the definition is not too important for this lecture, but I think you should know it at least, have an intuition. So this operator has singular values which I label with this thing here. So it's basically the largest of my operator. Okay. So somehow what this norm tells me is basically how much can this operator change a particular vector that you input. More or less things. There's also a trace norm. I'm going to define it a bit, maybe a bit differently than it appears in some places, but it's the following. So I have an optimization, operator B, and this operator has basically maximizing the expectation value. And the reason why this is interesting is because this allows us to, this is the measure we want to as a figure of merit for distinguishing quantum states. So a very useful quantity is the following. So I have two quantum states, rho and sigma. So I have the one norm between the two. And this somehow tells me how well I can distinguish the two states. Okay. Maybe probably some of you have seen this in some quantum information course, but I just wanted to define it. And also another property is, of course, for positive states. So if I have a quantum state, this is actually equal to the trace. And the other thing is another little lemma I want to talk about. It's called Hölder's inequality. And this is very simple. This is actually, if I have, I mean, it's more general than I'm going to write, but I'm just going to write the simplest expression. If I have one norm of two operators, this is actually upper bounded. Basically, it allows me to turn a product of operators into a product of norms. No? And the price I have to pay is that here I have one norm and here I have an operator norm. Okay, that's it. And then the other thing I wanted to define, actually, here. So I want to move to the other board. Is the Newton information? Okay, so probably, probably many of you have already seen the von Neumann. I'm just gonna write here. The von Neumann entanglement entropy, no? Like this. So there's this other notion, which is the Newton information. No? And you define it as follows: entropy of marginal A plus entropy of the marginal B minus the joint entropy of the whole state. No? So I have my state rho, and I have the marginals on A and B, and this is how I compute. And this is basically the sorry. This is how you define it. No? Is this okay, slides? And this is basically a most common measure of correlation. No, I guess you've already seen it in some lectures before. So actually, I'm going to put this here on the left side. I'm going to move to the left side. Okay, so let's start with the results. So actually, the first result I want to show you is, I think it's quite cute, and I actually want to show you the whole proof. Probably it's the only thing I'm going to prove in full, but I think it's quite a simple proof, so hopefully it's interesting. And it's an area law. For the area law, I need to draw a picture. So I have my system. Now I draw it as a 2D system. No? So importantly, I divide it into two, again, A and B. Sorry, maybe I'm calling A and B subsystems and operators. Hopefully that's not confusing. But these are subsystems now, A and B. Basically, an area law is an upper bound on the correlations between two different subsystems. No? Okay, and in particular, they have to do with the area between the two. So in my Hamiltonian, I have this region here, which I can call the boundary between the two. So it's just smaller than the whole system. No? Okay, yeah, so let's prove the area law. Okay, so actually this starts with a very trivial observation. So there's this thing which is called the free energy, which many of you already know, I guess. So I'm going to take rho AB to be my thermal state, okay, of my joint system. No? So this is now my Hamiltonian is this form, no? H of A plus H of B plus H of AB. Each of these terms is composed of local interactions. No? And as you can see, this one lives here, this one lives here, and this one lives in the boundary. Okay? So this is the thermal state of this Hamiltonian. This is the thermal state of this Hamiltonian. Maybe you all know the free energy of the thermal state is the lowest among all the states. No, in particular, is lower than marginals. So this is somehow a state in which I've just arbitrarily erased all the correlations. No. Okay, so let me just write this out in full. What is this? Energy of rho minus the entropy maybe it's smaller than beta trace of H of rho A tensor rho B minus the entropy of rho A tensor rho B. So I can arrange this a little bit. I can basically put this one in the lower bound and this one in this one here. And what I get is the following. I basically get the information. Can everyone see this step? So what happened here is that basically I have this term here, which is okay. I'm gonna move fast. Is this one here? And I have this term here, which is the first two of the mutual information, no? Because the entropy is additive, so this is actually the sum of the entropies. So you get the mutual information. And I have this thing here. This is an energy. Well, it's a difference of energies, no? So you can see this term is this term, this term is this term. Clear? There's a problem because H has support on the whole system. However, I can write H in this way. And the interesting thing is that actually the way we define these two states, basically these two states are the same here and here, but not here. No? So what happens basically is that the trace of H of A of rho is equal to the trace of the product. No? Right, and this is just because, to calculate this, I have to take the partial trace on A, no? So this is equal to this, no? So what's going to happen is that basically, when I put this expression into here, the contributions from this and this are going to cancel. Is that clear?
H on the right hand side.
H of A, sorry. Yes. Sorry.
Just to clarify, so these row A's, they are the reduced states, not the.
These are the reduced states, yeah. So it's somewhere defined below. Yeah. I write it again. Yeah, it's the reduced states. Yes.
Not the local thermal.
It's the local thermal state. No, so this is not equal to. It's really not equal. Okay, so what happens basically is that this is equal to this.
I is this
It's
H.
sorry, yeah, of course, it's the function of notation. The interaction term only. No? So now actually what I would do is apply this Hölder's inequality. I mean, there's some, you have to use triangle inequality and Hölder's inequality. But basically, this is a one norm. So I can also put one norm. Let me make it a bit slower. So this is basically smaller than the one norm in HAB and the rho AP and the product. I really don't
It's
speak.
getting very small. Can you
Yeah,
repeat
yeah.
it on the next board, maybe?
Change board, sorry. Okay, so this, I continue here. So it's beta, one norm of HAP, rho, plus, I can put a plus because I'm doing an upper bound. So it's like triangle inequality. And this is one norm, actually.
Special question. Is the last term, like in the upper blackboard, is this already the norm? How I don't really get this.
Yeah. So okay, yeah, maybe I should. Yeah. So this is a trace, of course. It's not a norm.
Yeah.
But actually, in general, the trace, but the trace is. This is true. And this is an inequality for positive operators, but this is not a positive operator. Because this can have negative values. This is the whole thing here. It's a difference. So. Okay, so well, this is so, and then I can use Hölder's inequality and this property here. And basically what I get is this. And this is the area law. So what this is saying basically is that I have my mutual information. This mutual information is upper bounded by this number. No? And this number grows with the boundary between A and B. It doesn't grow with the system size. No? So intuitively what this means is that the correlations in the thermal state, the correlations in two really big parts, they don't actually scale with system size. No? They scale with the boundary between the systems. No? So intuitively what this means is that the correlations are localized. No? Basically, A and B are correlated because they're coupled, but in a sense, it's only this small part of this small part of A. That is correlated with this small part of B, no? Because somehow the amount of correlations scales with the boundary, no? So it cannot be that the bulk is correlated with the bulk. Yeah, so you can see that this is a strong sense in which correlations are localized in thermal states. No? So you can see this is a way in which these states are really not very generic. No? They're simple. No? They're simple than some arbitrary states. No?
Sorry, I don't really understand why this has to do with the boundary. Like I don't see how the bound is Correct.
Yeah. Good question. Yeah, I'm being a bit sloppy here because, of course, yeah, it could be that, yeah, okay, it could be that, for instance, it's this part that's correlated with this part. No? It could be. Is that more or less what your question is about?
Yeah, I just don't see the relation between the bound and.
Okay, so, well, the point is that so this measures the correlation between all of this, and all of this, no? And what I'm saying is that this is bounded by the size of the boundary, no? So the thing I said next is that it's only this small part that is correlated with this small part. Actually, this is not true, but it's like the intuition that it gives you, because it could be that there's a case where this is actually not correlated with this, but somehow there's a place that is far away that is correlated with a place that is far away here, and this will be compatible with this bound. Maybe that's why you're confused, no?
No, so I think it comes from the way he broke up the Hamiltonian. It's a local Hamiltonian, so you have the local correlations at HAB. That's all the correlations between A and B, and they are at the boundary. That's why it grows with the boundary size.
Oh, okay.
Yeah.
So if you think it's only like next qubits are the ones that are sitting next to the.
Right, yeah, so this term, yes, this term only. So in this picture of the chain, this H of AB, maybe it is just a term here and a term here, right? And but it doesn't involve a term here because this one doesn't touch B.
So in this case, we would assume that there are only some maybe short-range interactions between inside the system.
Range.
Short-range interactions,
Yes.
because
Yeah. Here, I guess I've secretly assumed that the interactions are short range indeed. Yeah. I mean, when they're long range, maybe they decay. So you could take this decay into account when you calculate this norm. No? So maybe this converges. No, it's going to converge. No, if they decay fast enough. No? Yeah. Good question. Okay. Very good. Any questions about this? Okay, so I'm going to move now to a different kind of way in which the correlations are localized. So this area law tells you something, no? Which is that somehow the correlations are, they have to do with the boundary between regions, no? But there's a different sense in which the correlations are special in thermal states, no? And this is the decay of long range correlations. So this is, I would say, a complementary statement to the area law, because it tells you something else, no? Actually, I have to draw a different picture for it. So now I'm going to take my lattice and I'm going to take two subsystems. I'm going to call them C and D, and they are separated now by a distance which is L. Okay. Can everyone see this? Okay. So I'm not going to show the proof of this because it's actually much more complicated. I don't have time to do it in 1 hour. But it's similar, no? So you have the meter information, and now it's only between regions C and D. Okay. So now you have to look, when you define this, you have to look at the marginals on these two regions, no? So there are small subsystems. So typically, I mean, I will say what typically means in a second. What's going to happen is the following. So you have the boundary of C and the boundary of D, and the size of the boundary. Well, maybe there's some constant here. I don't care about what it is.
maybe not DEC again.
Yes, thanks. Okay. So this is just the size of the boundaries. It doesn't matter too much. But what matters is that the correlations actually exponentially. And this is this is important to know. This is a correlation then. So what this is telling me is that the correlations between systems that are far apart are very small, no? So actually you can go back to this picture and think of the area law again, no? Because in the area law I said that this may be some particular case where this bound is compatible with this part being very correlated with this part, but this property rules it out. No? This decay of correlation property rules it out. So the two of them together, more or less, really tell you that the correlations between the systems are localized. No?
Excuse me, when you talk about length L, are we still on a lattice and it's just the amount of particles in between?
Exactly, yes, the amount of particles. Yeah, I should have said this better. Yeah. And then this is some typical time scale. This is an upper bound, so it may be actually there's different correlation length in your system, but this would be like the shortest of them for the bound to work. So this holds in two cases. This is known to hold in two cases. When the system is 1D. And in any
A little bit lost. So can you explain again what is the norm of this, like the boundaries?
yeah, it's just so you have this region, no? And this region is made of it's like particles inside, no? So it's somehow counting the number of terms that lie in the boundary. No? And if you want, you can somehow since this is an upper bound, you can more or less overcount it. No? Maybe you can count the ones that are just outside, which maybe are a bit more. It doesn't matter too much. No? It's just that it has to scale like some sense, like the boundary in some sense. No? It has to be completely. I mean, for these statements, it's inequality, and the thing that matters is this. You can sort of overestimate this a little bit.
But we're working in 1D then. It's one, no?
So this holds for one in one dimension, but also in more generally. Yes, so in any dimension, but for high temperatures. So there exists a threshold temperature, which is beta star, and people have put like bounds on this, like a upper bounds on this. That's that. For any thermal state at a temperature that is yeah, that's right. Yeah. That is lower. No, it's higher. Sorry, than a threshold temperature. No. So high temperatures means less correlations. No, this is the intuitive thing. No. For instance, beta 0 is the maximal limit state. No, so this is product, of course. So for any thermal state that obeys this property, this holds. Okay, and you can maybe relate this threshold temperature to this correlation length. Like this, no?
It is true for any correlation, so it doesn't depend on interaction Hamiltonian HCD.
You don't. Yeah. So A, there's no term that couples directly C and D. No.
Oh.
No. So here, so these are very far apart. No. So I'm gonna have so I guess I can call this region A. No. So yeah. So the Hamiltonian will be like H of C plus H of D plus H of A plus H of AC plus H of AD. Yeah, so this interacts with this interacts with this, but they don't interact directly, And that's the reason why the correlations decay, Because I mean, basically the idea is that the thermal state is the exponential of the Hamiltonian. No? So presumably, since the Hamiltonian is local, the exponential of the Hamiltonian is going to inherit some of the locality properties. No? Of course, it's not the same because you take the exponential, so it's more difficult. But at least for high temperatures, it holds.
Two questions from the internet.
Yeah.
So, in general, the correlation length and this beta star, do they depend on the Hamiltonian?
They depend on the Hamiltonian, yes. So they depend. So, for instance, when you think of proving these things, you're going to put bounds on all of these things, no? So maybe you put an upper bound on this, and maybe some upper or lower bound on this correlation length, and they will depend, for instance, on. So when you have so in my Hamiltonian, I was writing it as a sum of local terms, no? So they might depend on things like, for instance, how strong each of these terms is, no? What is the norm of each of these terms? And it will also depend on things like how many particles each of these terms couples. No? Because the more terms each of these couples, the longer the correlations will be, the longer range they will have. No? So yes, all these things. Yeah, of course. There's no universal expression for this, and actually, this depends on the particular Hamiltonian. Yeah. It's just that you can write a universal expression that you can apply to any Hamiltonian. Yeah. Okay, so
this relation that you've written down implies like a trade-off between the size of the boundary and the distance between the two systems. So I can always make this correlation as big as possible. If they're very far apart, I can increase the correlation, but just having a very large system. So just increasing the boundaries. So we have like two galaxies that are very far apart because the galaxies different.
Yeah, and I guess that highlights also why it's interesting that this is exponential. because the boundaries are going to have to be huge, no? Because exponential is gonna dominate, no, quite often, no. Okay. So basically, if you take L to be some, like a tenth of the system, then yeah, this is gonna dominate, no. So the thing is that this exponential decay basically holds in these cases. And the point I want to say is that this correlation decay is actually related to the lack of phase transitions. No? So in thermal states, you have phase transitions. No? Like maybe some of you have studied this 2D icing model, no? And you can solve exactly the one. No? So you can reach a temperature where your order parameters change and you have a phase transition. No? So at the phase transition point, this property does not hold. It might hold with a polynomial decay, actually. So the correlations are like don't decay as fast, no? But an exponential decay basically tells you that you're away from a phase transition. No? And the interesting thing is that actually this property is related to many other things, no? So in particular, since it has to do with the lack of phase transitions, it also has to do with the partition function being analytic, for instance, no? Which has to do with the lack of phase transitions also, no? And it has to do with, so for instance, if this holds, you can show properties about the heat capacity, no? So the heat capacity is going to be bounded by something, no? It is not going to diverge. Just from this property, you can show it. Or for instance, I mean, there's even other things you can say. So for instance, this is a statement I like. Maybe some of you know the central limit theorem, no? Which is telling you that when you toss a coin many times, your distribution is going to be like a Gaussian, a very big Gaussian, no? With some variance that is small, no? So from this property alone, what this is telling me is that, for instance, my energy distribution behaves a bit like tossing coins, no? Because when I measure the energy in different parts, the correlations are very short, so they're more or less independent, no? So from this, you can, for instance, show that your energy distribution is actually like a Gaussian. And this is thermodynamically, this is relevant, no? Because, for instance, this is related to this phenomenon of equivalence of ensembles, no? Because if my energy distribution is a Gaussian, so this is my gift distribution, and it's a Gaussian because of this property, then you can also maybe you can also approximate it with the macrocanonical ensemble. No? So this looks a bit stupid, but it actually works. But you can prove that these two distributions somehow look similar. No? This is the equivalence of ensembles, and all these things are related in the end to the decay of correlations, actually. Any questions about this?
So when you have a system that has phase transition, this is no longer hold?
It should not hold. I don't know if there's some exotic case where it will hold, but it should not hold. No. And I think you can make this quite rigorous mathematically, because when you have this kind of property, it also follows that you can somehow compute the partition function. And the reason why you can do this is because it's not analytic. No, it's analytic. Sorry, it's analytic. So this is related to the analyticity of the partition function. So this means there's no phase transition. No? There's no divergence in the order parameters, no, and so on.
I was thinking about that in the example, for example, in the 1D and 2D icing model, because in 1D it's analytical and you don't have phase transition. But
yeah, so that's why it always holds in one dimension. No? So in one dimension, there's no thermal phase transitions. This is what this is telling you. No? In high dimensions, there are phase transitions, but only below some threshold temperature. Right? And this threshold temperature is somehow universal. No? And like all the models are going to have if they have phase transitions, they will have them below some temperature. You can estimate. Yeah. I mean, then this bound probably for some models is not going to be very tight, no? So it's not going to give you a very good estimate. No? But we're making general statements here. No? So, yeah. Oh, very good. All clear here? Okay, so actually now I actually have time to say something I was thinking of maybe saying, maybe I don't. And it's actually a more quantum information-y topic that is actually a strengthening of the two things I've told you already, but it's a bit more difficult. So I just hopefully can use the last, I have like 10-15 minutes left.
Yeah, 10 minutes.
Okay, so I'll try to tell you about this. And I want to tell you about this because I think it's a powerful topic. It's a purely quantum information concept, and I really like it. And probably many of you have not seen this. Most of you have not seen this probably. So this goes under the name of the quantum Markov property. This is going to be a bit trickier, so let's see how much. How many of you have heard of the PETS map and the quantum Markov states? Okay, so there's a quantity which is very important in quantum information, which is the conditional mutual information. And this is defined in terms of free systems, okay? And it's actually the following. Where is it? The difference of mutual information, okay? I will draw a picture in a second. Okay, so this free system now. What you need to have in mind is perhaps something like this. So I have system A here, system B is around it, and then system C, okay? And in 1D, well, you can see that it's basically will be something like this, you know, like A, B, C, no? So this quantity actually is, I mean, it's a bit tricky to interpret if you haven't seen it before. But what it's telling me is basically how much are the correlations between A and C mediated by B, okay? So what it means is that if this quantity is small, it means that the correlations between A and C are really correlations between A and B and C, okay? So you can see that, you know, this is the information that A has about BC, and then I'm taking out the information that A has about B. No? So, you know, somehow it has to be really just purely information between A and C. And of course, this is not equal from to design, just to here. It's something else. No? So actually, I mean, this is a super nice concept, and it's behind many quite non-trivial quantum information ideas. No? And the thing is that people have studied this in the context of thermal states, no? And very interesting.
Can you just clarify if you're saying that this holds for all states, or?
I'm not saying what holds for, well, so okay. So the fact that this is small does not hold for all states, no? And in fact, if you take a typical state, it's not going to hold, no? And there's a class of states that is very particular, in which this quantity is 0, for instance, no? And this will be the systems in which, you know, A is correlated to B and B with C, but somehow A and C are correlated, but only through B. No? And this is exact. And you can make this approximate by this quantity being small and but not 0.
People are asking to speak a bit slower.
Oh. Okay, so in thermal states, people have studied this quantity and in the same context as these two. So in 1D, there's a paper by Cato and Brandao. And they showed the following. They showed that this quantity is superbounded by, what this means in a second. So I have, actually the square root, not important. But so this means that basically I have a exponent here, and this grows faster than square root of B. Okay, this is what this means. This is like this big O notation. So I mean, just think of this maybe as, you know, something smaller than e to the square root. And this quantity here is basically the no, sorry, maybe I should write something else. I think maybe the better way to write it is the distance between A and C. Okay, so you'll be something like, for instance, the distance between A and C. No? So this has to do with the size of B. No? And in one dimension, they're the same. No? The size of B and the distance are the same. So basically, what this tells me is that if I make the B system quite large, but in fact not too large because this is exponential actually, this quantity is going to be close to 0. No? And what this means is that somehow A and C are, you know, only correlated through B. No? And actually, this is really the strongest sense in which correlations are localized, can be localized. I mean, I don't know if it's the strongest sense overall, but it's definitely the strongest sense that people know about. No?
Can I quickly ask something? By distance between A and C, you just mean the amount of atoms that are.
The atoms, yeah. So you will take, I mean, I guess there's many distances here, so you will take like the smallest. Yeah. And then, yeah, so this is for 1D, and for high temperatures, so above a threshold temperature again. This is a paper by Uhara, Cato, and Brandao, where actually they show a similar thing. So this, you know, so for instance, there's one cute thing you can do is that this statement is actually stronger than the decay of correlations. because I mean, if you define this the proper way, which maybe I haven't done completely, you can take B to be a trivial system. So if you take B to be trivial, so you take it to be 0 particles, and but A and C are still far away. This thing collapses to the emitter information, no? Because this will be 0, and this will be the emitter information between A and C. And I've told you that this decays exponentially. So the correlation follows. But somehow it's also telling you that there's some sense in which these correlations are very strongly localized, no? Yeah, and one reason why this is interesting actually is that well, you can see again that these things hold away from thermal phase transitions, no? So because this is in 1D and for high temperatures, which we've established has to do with lack of phase transitions, and also this is related actually to ways of preparing a thermal state, no? So there's some other results which I mean I don't have time to go into, but what it's telling you actually implies that the correlations are localized means that you can reconstruct your thermal state somehow in a local way, no? So you can think of a chain. So imagine I start with a part of a chain and I call this A, and I want to reconstruct it with some quantum maps, no? So actually this is telling me that I can somehow start reconstructing the chain by acting sequentially. So I can maybe do some physical operation here, and I start reconstructing the thermal state, and I can carry on. No? And so what I'm saying here is that yeah, somehow you can sort of build your thermal state out of small building blocks, no? And of course, this is related to correlations being localized, no? Because you're acting very locally. No? And this is related to, for instance, quantum algorithms for preparing thermal states, no? So the fact that this holds probably tells you that there's efficient quantum algorithms for preparing thermal states, and the way you will do it is somehow a sequential preparation. No? And it's also related to tensor network approximations to thermal states. No, so for those of you who know about tensor networks, the fact that you can somehow, prepare a thermal state in sequence is, I mean, if you have in mind this picture of matrix product states, for instance, no, so there are states that you can somehow also describe sequentially, no. And this means that the description is very simplified, no, because you don't have to, diagonalize the whole matrix, but you can just do it sequentially, so you can do it efficiently, no. And so this property actually guarantees that you can approximate your thermal state with tensor networks. And yeah, you can actually make this reasonably rigorous, actually. And perhaps this is a good time to stop.
Do you know the method they use for the high temperature expansion?
Yes, is the link cluster expansion.
Okay, so like a quantum cluster expansion.
What, sorry?
Like a quantum cluster expansion.
Yeah, exactly this, yes. So this, for those of you who don't know, is basically expanding the Hamiltonian into a Taylor series, and then each of these terms you sort of count how many clusters you have. Yeah. And then this expansion only converges for high temperatures.
Super question, but so how is this a new result? I mean, this cluster expansion, high temperature expansion of the quantum systems is known since the 80s.
Yeah, but the fact that this follows from the cluster expansion is non-trivial.
Okay.
This is, I mean, take some work. Yeah. So with the cluster expansion, you're approximating your thermal state by a different operator, and then you have to compute this quantity for this operator, and this is not necessarily trivial.
So this critical temperature, what does it depend on?
It depends on, well, it's not clear, no, because people have bounds on it, and the bounds depend on, so it will depend on, in particular, I guess, in two quantities. So when you define your Hamiltonian in this way, and you have two constants that are important, So for instance, one is usually called J, and J has to do with the largest norm of any individual term. And there's another quantity which is K, which is actually how many, and this is so this has energy units, this has no units. So this is the number of subsystems that each of these terms can couple. So for a two local, this will be 2. For a model, this will be 2. And then if you have long range interactions like with exponential decay, then you have more constants, like the decay rate, for instance. And yeah, and of course, but of course, this is part of a this is more part of the technique that you use to prove the bound. No, it's not necessarily the fundamental thing in all systems. No, so.
Can you use this to show like uniqueness of a uniqueness of infinite volume Gibbs states?
Well, sorry.
Can you use this to show uniqueness of infinite volume Gibbs states in the
Infinite volume. Right. Yes, I'm not sure how. Does this follow from the analyticity of the partition function in the limit?
Yeah, I mean, at least in the classical lattice systems, yes.
Yeah. So, yeah, that's a good question. I don't know. So actually, one thing I haven't said is actually this property is actually what I find is quite different in from classical and quantum classical systems. This quantity is always zero. For quantum systems, it's non-zero, and actually this matters sometimes. No? So somehow for classical systems, things are a bit simpler. In this, like the relation between these and other things is simpler in classical systems. If you have approximations, it's more complicated.
Very good. We get 15 minutes break. Thanks, Alvaro. let's restart.
Before that, I'm gonna erase. Okay, so I more or less told you everything I wanted to say about the correlations between different parts of the gift text. Now I'm going to talk about a topic that is somehow complementary. And actually, that's the reason why I wanted to talk about this specifically as opposed to something else. And it's because what I'm going to say now, which is basically about subsystems. Systems. Of thermal states, of course. My hope is that I show you some facts that are general and also maybe they are useful in whichever quantum thermodynamic problem you are tackling. Because I guess many of you work in different approaches like theorems, visual theories, whatever. It's a way of thinking of let's say strongly coupled thermodynamics, from the perspective of a system. Okay. So in the previous lecture, of course, as you've seen, I've talked about correlations, So I've talked about different parts of the system, and I'm also going to talk about different parts, but focusing on one. So the picture now is this: A and the complement of A. So everything I want to say now is about the following state. Marginal on subsystem A, which may be small, maybe large. In general, I think it's probably easier to think of a small system. The first thing, just so that we're all on the same page, when you're your Hamiltonian, this is going to be as before, h of A plus h of B plus h of A B. It's very important. It is not equal to this. And of course, the reason for this is that there's interactions, and these interactions may be strong. When you study things like open quantum systems, typically you have a situation in which this interaction is small. So in the decoupling limit, you can actually approximate. You can actually make this approximation. But somehow, when you have a strong coupling, which is maybe it covers a whole different range of physical situations, you just cannot make this approximation. And somehow the fact that you cannot, I think, complicates a bit statements that you want to make in dynamics, maybe, or other things. But I guess what I want to explain now is that actually, even if this doesn't hold, approximate versions of this hold in spin systems. And these approximate versions have to do with the locality of the Hamiltonian. And you can maybe hope with these results, you can hope to make maybe even some calculations about these marginals. You can use them for different things. Okay, so this so I don't think this is completely established in the literature, but this topic in my mind goes under the name of locality of temperature. And I guess the general principle is, how do we think of strongly coupled subsystems as thermal states, And how does the global temperature manifest locally? That's more or less the question. Side. So I would say there's in the literature, or as far as I know, there's two complementary ways of answering this question, and they give, they are basically slightly different takes on the problem. So I'm going to talk about the first. So the first is the Hamiltonian in force. And I mean, the idea is very simple. So, we've established that that doesn't hold. However, any state is a thermal state for some Hamiltonian. So there's this thing called the Hamiltonian mean force, which is just the following. Let me see. I get everything right. Okay. So basically, I take my exponential of the Hamiltonian. I look at what happens in subsystem A, no? And I take the log. No? So it's somehow just taking the log of this state. No? I mean, here I'm not caring about partition functions because I just care about the Hamiltonian. About normalization here. But hopefully this is, I mean, is it clear what this means? So it's just some operator, no? And of course your state is the exponential of this operator, definition. Yeah, so people study this in different contexts, no? Any questions about this?
So what's the title Hamiltonian of mean?
Mean force. Mean force, yeah. So like average force, I don't know. I didn't name it. I'm not even sure I like the name, but yeah.
Inside the trace, there's no Z, there's no partition function there.
Well, because I'm just defining a Hamiltonian. No, if I was to define a state, then I would have to be a bit more careful with the. But I guess yeah, because I mean, just think of the units, no? Well, I guess the set doesn't have units, no? But I'm taking this is a trace of exponential of a Hamiltonian. I take the log, so it should be a Hamiltonian, and then I have the beta minus 1 to get rid of this beta.
Partition function is just a constant, right?
Yeah, just a constant. I mean, I could also define it with a partition function, but this probably not helpful. Yeah. Okay, so yeah, so I guess it's interesting to study what this is. No? Okay, so let me see if I can give an intuition. I need to draw a picture. So in particular, one interesting thing is what's the difference between these two? And the difference between these two, I mean, probably you can guess that locality is going to play a role. No? Because imagine I have my state system A. And A is like a small part of the whole system, but it's still kind of large. No? Many particles. No? So you can imagine that since the correlations are localized, since my Hamiltonian is local, whatever, the Hamiltonian, these two, over here in the middle, away from the boundary, will be similar. No? And maybe here near the boundary, since the effect of the interactions is stronger, they might be different. No? Because of course the difference between this and this only happens because I have this interaction in the Hamiltonian. If there's no interaction, if the two are the same, there's no problem. Okay. Okay, so here's what people can show. There's some open questions along these lines, so I encourage you to read more on this. Actually, I can talk about this later. But this what I'm going to say is actually from a paper that I mentioned before. This Kuhara, Kato, and Brandon. Because actually, for some reason, that is a bit difficult to understand. This is actually related to the Markov property that I said before. This is very not obvious, and I don't think I understand the connection completely. You have to go through the calculations. But the two things are related, no? Like the proof you need for one is useful for the proof of this. This cluster expansion that someone brought up. Anyway.
Which property do you say?
The Markov property. So the decay of the last thing I said in the previous lecture of the decay of the conditional mutual information. This difference of mutual information. Okay. So the thing is now I can take a ring. This in 2 dimensions, but of course you can do this in 1D in any dimension. No, it's in 2D, it's easier to draw, I guess. Okay, maybe I'm going to draw this big. So again, I'm going to have. So now somehow I'm dividing. Well, sorry, subsystem A is all this. Okay. This is A. Okay. What I'm saying now is that I'm taking somehow region that is near the boundary between A and the complement of A, right? And this region has distance from some fictional boundary, let's say that is L. Okay. Sorry, this is small maybe. Can anyone more or less understand this picture? No. So I'm just taking a region which is like a ring which is somehow near the boundary. It's still within A, but it's near the boundary between A and the rest. Okay. So basically, the idea is that you know, the difference between this and this is basically supported here, right? Okay, let me see. So let me see if I can make this precise. So so I can define this as an operator, okay? And you know, intuitively from the decay of correlations and other things that you know, you can maybe understand, this operator should have very small support, meaning it should be very close to the identity here, away from the boundary. Okay, it should be far from the identity, near the boundary. No, so this is what you can show basically. And you can show that, and this is okay. So you can show the following, and maybe I should say this a bit slowly. I'm going to introduce a different operator, which is this. Okay. And the feature of this operator is that somehow it's similar to this, but it only lives in this region. Okay. Yeah, sorry, maybe the orange region. Okay. So it doesn't have support. No? And there's and I define it in terms of L, of course. No, L is a number that I can choose. Actually, I can choose how large I want to take this or not. No. Yeah. And yeah, so basically, yeah, so this is the identity here. No? Okay, so what you can show is that, or again, for high temperatures, it's actually okay. There's some constant here. Okay, maybe I can pull out the whole thing. There's some constants, and there's also this thing, which is the boundary of A. So a boundary of A meaning the size of the boundary, and then it's the following: beta over beta star. So write it bigger. Beta over beta star to the power of L, and then 1 minus beta over. So this is the result, okay? So okay, let's go through this a bit more slowly. So this is number, beta versus beta star, that because of this condition, this is smaller than 1. No? I'm taking powers of it. So the larger the L, the smaller this is, okay? Exponentially small, no? So it decays very quickly. So the point is that what's happening here is that I can choose an L, and what this result tells me is that I can find an operator, this, which approximates the difference between the two very well, and it only lives on the boundary. Okay.
How do you construct this operator?
Yeah. So it's difficult. Yeah, I guess I'm not telling you what it is, but so this has to do with this cluster expansion that was mentioned before. And yeah, so there's an exact expression you can write, and in principle you could like compute a code to calculate it. There's no simple expression, but let me tell you that. Okay, I didn't write this down. I'm not going to be very precise, but somehow this is this operator. You can write it somehow as a sum of products of how do I say this? Of products of small terms in the interaction, and these terms have to do with the interaction Hamiltonian. So somehow maybe this is like something to do with the trace of. Okay, I might say something completely wrong, but it's something to do with the operators that live the interaction terms of your local Hamiltonian that live in the boundary. Okay, so you have a product of many of these things. No? So this is somehow so when you write this down from this expression, somehow you can write this as a Taylor expansion of the logarithm. So well, you can write it as a Taylor expansion in beta. Okay. And once you do this, you somehow get that this is like a sum of products of local Hamiltonian terms and so on. And the point is that this expansion, this Taylor expansion, you can cut it at some degree. And this degree is L.
Okay.
So what happens is that when you choose an L, what you're choosing is a number of terms in this product. And basically this number of terms maybe couple this, and this, but not. Yeah, so that's how you can calculate it. And the point is that actually the reason why you need this threshold temperature is because when you do this Taylor expansion to infinite degree, this expansion only converges for beta small. For beta large, it's like it's somehow like it's like adding so it's like so basically what you this expansion you can bound it by a geometric sum, and this geometric sum gives you this. I mean, if you can see this is actually related to a geometric sum. No? So when this condition holds, this geometric sum converges and your error converges. Otherwise, it doesn't converge. So yeah, so this is actually the reason why you have this and this actually. Because if you take it to infinity, then you have this. Well, you have 0, but 1 minus this will be the sum of the geometric sum. Very good. So yeah, so basically this is the result I wanted to show, no? And the idea is that this is pretty general. No? This holds for any local Hamiltonian at a threshold temperature. It may be the case that before I was telling you that many things hold for high temperatures and 1 dimension. It's probably true that this holds for 1 dimension also, but this is open. So as far as I know, it's open. Okay. And yeah, I guess this is one reason why I think this is interesting is because this is really telling you about what is the Hamiltonian of your subsystem, no? Effectively, no. So hopefully you can do things like compute heat flows or work, or maybe define fluctuation theorems with respect to this Hamiltonian. No? And of course, it's more complicated, but maybe it's doable. Okay. Any questions about this?
Is L like a number or is it?
So L is an integer, yeah. Well, it's number, yeah. And basically L is a number I can choose freely, no? Because basically the bigger I choose the L, the smaller this number is, so the smaller my error is, but the larger the support is, no? So somehow there's a trade-off, no? So I can choose an L that is large, and this is good because it gives me a small error, but then my operator is going to be quite big. And then if I choose L that is the opposite, no, it's kind of the opposite. So in practice, when you use this kind of statement in your results, you have to be careful with this trade-off, no? So so it happens sometimes that when you try to apply this to a particular problem, no, you're gonna have different you're gonna have different errors in when you do the calculations, no? And in the end, somehow this maybe forces you to choose a particular L, no? So maybe L has to be like half of the distance between of the size of A or something like this. So the point is that with this result you can choose it, and when you apply this result, you can flexible, no? So and depending on the problem, you can choose one thing or another. No? Thanks for the question. Yeah, so basically when you compute a heat flow, no, or a work from this thing, you're going to compute it up to some epsilon error. This epsilon error is going to be this. No? So effectively, what you have is a trade-off between epsilon and L. Any other questions?
How does this now relate to the initial question we had regarding locality of temperature? Or can we now make some quantitative statement regarding it with this result?
What result?
Can we now make like a quantitative statement regarding this inequality we had at the beginning? Or like, are we able to state this inequality you gave there on the top?
So even this.
Exactly. So you're trying to.
I guess I'm trying to see how far is this from being true, no?
Okay, so that's the measure for how strong these two are not equal.
Yeah, exactly. Yeah. So because of course the difference between the two Hamiltonians is this operator. So I guess the difference is going to be the norm of this. I guess I'm not really saying that the norm of this is going to be small because maybe it's not. What I'm saying is that the support is localized. And maybe, when the couplings are weaker or something, the norm of this is going to be smaller for sure. And maybe the norm is also, maybe the norm of this is also small in some sense because it's also localized. No? So if this is actually, if L is not too large, then yeah, maybe the norm is not too large. So yeah. So yeah, I guess maybe you could translate this into found on how much the two is there. I guess this will be related to this, but this by itself I think is already maybe the interesting part also. No? So yeah, it depends on what you care about, I guess. The question you care about exactly.
Just one question, I think it relates to this small, the, I mean, you said that L goes to infinity. Because it's the extension there. And doesn't this, I mean, how does this relate then to the image of L being bound between a given region of A and to the boundary, you know? Because then L should be finite.
Yeah, you cannot take L to be very large. No? Yeah. Well, so the thing is, well, so first of all, this is, so when you do these upper bounds, you know, maybe you have just a sum that goes from L to like some big number, which is maybe your system size. But then since you're looking at upper bounds, you can take this to be infinite. You know? And then let me see. So I guess, yes, I think in general that's what happens. No? Your system is very large, and the number of particles is n, big N. No? So I guess presumably you could have some bound, well, yeah, maybe L. Physically speaking, you can only take it to be as most some function of n. But this is the beginning of the problem. And when you define these things, then you have to upper bound this by some mathematical expressions. No? And these mathematical expressions might contain big N. But big N, you don't know what it is, effectively is infinity. So you can just take it to be infinity. And since we're,
the thermodynamic limit.
Yeah, and since we're looking at inequalities, I can add more terms, and this is no problem. No? And the only thing that matters is that this thing converges. No? Because, I mean, effectively speaking, I can get an error here, and I really don't care whether it's infinite or it grows with N. It's kind of, I mean, either way, that this thing is not what I want. No? So actually, this statement I think is nice because it somehow illustrates the way a lot of analytical statements about many body systems work. No, it's like you somehow have like some notion of effective locality, no, and then you can choose parameters and so on. So for those of you who have worked before with things like Lee-Robinson bounds, no, so the Lee-Robinson bounds is basically like an effective light cone of the dynamic. The unitary evolution, and this unitary evolution has a light cone, no, and basically you can choose, you know, in the Lee-Robinson bound there's an error, and then this error depends on like how big you want to take your light cone and so on. So this sort of argument with choosing L and so on is actually related. Okay, so maybe now I can move on to the other thing, which actually I wanted to prove, but I don't know how much detail. So the other thing is it's kind of complementary, I would say, and it's called. I mean, actually, this name is even established. It's called local indistinguishability. This is how I called it. It's different. So now, again, I care about the marginal. Right. But I don't want to compare. I don't want to look at the Hamiltonian of this. I want to look at something else. Because now I'm going to draw a picture. Well, it's kind of the same picture, but what I mean is different. I have A, I have B, and I have C. Okay. And I can write the Hamiltonian, of course. A plus B plus C plus H of A B plus H of C. And I'm going to define another Hamiltonian. I guess I don't want to call it H. Okay, H prime. H of A plus H of B. So actually, what I want to compare is here now I can write BC here. This. So I have two thermal states, one which is defined in a very large system, and another one which is defined in a much smaller system. No, in particular, it's basically a thermal state with a Hamiltonian that only contains the terms that support on A and B. So I just forget about C. It's much smaller. How small? I can choose it. How small I want. Okay. So we want to look at. So as I said before, the way to distinguish quantum states is with a one norm. So I want to upper bound this. Okay, so I wanted to prove it like in full, like all the steps, but I don't think I have time to do this, and it's probably a bit boring. So for those of you that care about this is actually proven in the notes. And actually, I should change the picture because what is proven in the notes is not for 2 dimensions; it's actually for 1 dimension. And that's what I'm gonna do, where A here, and C here. I'm actually not. Oh, I need to say something. So right here. So A is like at the end of the chain, B is next to it, and C is like the rest of the chain, which could be super large. No? Okay. So, okay, so I start with, so I'm going to do all the steps. Rigorously, to do it rigorously, you have to care about, basically you have to do triangle inequality many times and Hölder inequality, but hopefully you get the idea. I'm just going to write what I wrote earlier. And actually, I'm going to define this a bit differently. I'm going to write a state. So this is my original thermal state. And I'm going to write another thermal state, which I call rho A, B, tensor rho C. And I trace out B and C also. And basically, this is, I mean, it's the same thermal state where I just take out the interaction. So rho B tensor rho C is equal to e to the minus beta h prime plus h of C. And of course, because there's no, basically this, the difference between this and this, the difference between this and the Hamiltonian is that I've taken out this interaction, okay? So this is a product. So these 2 things commute, no? And they have different support. That's why I can write it like this. Okay. So I can write the definition of the 1 norm. So this is basically the from like the previous lecture. So I can optimize over expectation values. Trace of, so now I define an observable O of A, and I have the difference between these 2 states. Okay. Now the particular thing is that since I'm looking at subsystems, sorry, and this is equal to this by the definition. And the thing that is particular now, that this observable has support only on A. And the reason for this is that here in this 1 norm, I only look at marginals on A. Okay, is this clear? Yeah, so you have just support on A. So now I want to define an operator, and this is quite important. I call it EBC. And it's the following. Beta H minus beta H minus H B C. You can see this is the Hamiltonian state. No, state. Okay, where I take out the interaction. So somehow you can see that because these 2 things don't commute, I cannot cancel this with this. No? But I really want to cancel this with this, no? And then only get, and then maybe get something like e to the beta h of BC. No? I really want to do this, but I cannot, no? Because they don't commute. So the point is that you can somehow make this approximate. Okay. So the reason why I care about this operator. Okay, this is the definition in case someone forgot. The reason why I care about this is the following. With this operator, I can basically transform this state to this state. So there's this identity that is, I mean, it's simple to see, hopefully, which is that I can write this thermal state as a product of this number. This is constant, okay. And this is operator. Yeah, this is just because exponentials cancel. Okay. So now I can put this into here. So let me call this. Let me carry on here. This proof is not boring anyone. So this thing is equal to the expectation value of A of rho minus. Okay, and here's where it gets interesting. So that's a result. So this thing. I mean, maybe I just write it again. This is important. This operator, you can ask the question of where does it have support? No? So you can see that it has support in the whole system. No? It has H. No? So this operator has support on everywhere. No? However, it has support everywhere because this thing and this thing do not cancel. No? And the reason why they do not cancel is this term. However, this term is very small. It's localized, no? Because this term lives here. Maybe and if this wasn't there, this will cancel, no? So the point is that you can do an approximation, and this is a very, I mean, this is part of a famous result by Araki. This is super old. This is 69. This has to do with thermal states in 1D and lack of phase transition and so on. So what Araki showed is that this operator can be approximated by, and it's similar to what I was saying before. No? You can choose an L. It can be approximated by an operator that lives here now. This operator lives. I don't know if you can tell the blue very well. This here. What is this region? So this region has a size, well, the distance between this and this is L, right? So it's a bit like before, no? So now this operator does not act on the whole space, no? It acts only on the vicinity of the interaction, okay? Is this clear? It's kind of like before, actually. So somehow this is doing undoing a thermal evolution and then doing it again. And what I'm saying is that this undoing can be approximated by something local. And actually the exact statement is complicated, but it's constant, and then it's like some number to the power of L, and this is higher than 1, but then you have a factorial. So the factorial wins over the exponential. So this is basically this decays exponentially with L. You can think about this. Okay.
What is Q? What is Q?
Q is some number. Q is number. And K is their constants. And the constants depend on parameters of the Hamiltonian and so on. But the important thing is that this decays with L. Okay. Let's carry on. So the point now is that actually maybe I just moved to a different board. So the point now is that I can approximate the thing with the following. And I'm going to write the symbol. If you want to write it properly, you have to do inequalities and triangle inequality and so on. This is in the notes. This is the only thing I changed. I put the L here. And there's some error here that has to do with this error. Okay. Okay, but this is interesting now because now this observable act on different regions. Okay, so let me rewrite this. This is trace of a rho minus trace of A rho E. So this is now interesting because now these operators act in different subsystems. So I can use the thing from the previous lecture of decay of correlations. Okay.
Are you still maximizing over OA?
Yes, I am. Sorry. Yeah, I guess I forgot at some point. Yeah. Yeah. So let's say OA is the one that maximizes the maybe I can call it OA star. And it's the one that maximizes the one norm. And after that, I can forget what it is. It's just some operator. So you can use the decay of correlations property of the middle information. And basically what this tells me is the following, is that the trace of OA rho, and I can solve them because of the cyclicity of the trace, no? And also they have different support, so they commute, no problem. So this is similar. The trace of OA rho times trace of AL BC rho. Yeah, so this is just from the decay correlations. Basically means that the expectation values are, they're independent, they're decoupled. So you can approximate this with this, and this is an approximation, and this approximation is going to depend on this correlation length that I explained earlier, and so on. No? So again, if you want to do this properly, you have to take all these errors into account. Okay. So write this here. This is nice, no? Because going back to the thing that we're trying to prove. Now we've gone one step further. Basically, we have trace of rho, and then I can take this out as a common factor. So this is an independent statement. This is not part of the chain of the qualities. Trace. Okay, so what's happened here is that this term I split it into two of this, and then I can take this common factor out. No? So I have one from this and this from the contribution, no? And I have the partition functions also from this. No? Okay. So now you can go back to the definition of this, and basically this approximates E. Hopefully you already see what's happening. Maybe I use the other word actually. Where was I? Okay, so I have one minus. Let me write it differently. A trace of rho. Here's where we are. But now we can do the approximation of Araki again, this one. And apply it again. Here. So basically this approximates the trace of rho. Yeah, and you make an error, and the error again has to do with this error of hierarchy. But what is there's a partition function that comes from the denominator here. Does this work? Yeah. So there's an e to the beta h here, which cancels the denominator here. No, the numerator. Sorry, and I'm left with the numerator, which is so basically I get the trace in the numerator. I get the trace of this operator. The trace of this operator. If I define it properly, it should be this. Yes. So this is the inverse of this. This is approximately 0. Anyone lost or following? Okay, so let's recap. So we've shown that this number is close to 0. And what is this number? So we can now go back to the chain of inequalities, well, the chain of approximations, no, which is this. So what we've shown that is close to 0 is this thing, which is so basically what we've shown is that you can approximate the marginals of a thermal state, of a huge thermal state, with the marginals of a much smaller thermal state. Okay, how small depends on how much you want your error to be, because how small depends on L, no? And the idea is that now I can choose L however I want, and the way I'm going to choose L is basically half the size of B, no? Because now the reason for this is that L, the larger I choose the L, the smaller this is. But also the larger you choose the L, the closer this operator and O of A are going to be. So the decay of correlation is going to be it's going to give you a larger error. So there's a trade-off here, no? So you have to choose an L such that this is small enough, but also such that the decay of correlations also gives you a small enough error, no? And I mean, maybe you cannot see this very well here, but if you do the proof in full, basically what happens is that each of these steps introduces an error, no? Depending on what you used. So here I used hierarchy, here I used decay of correlations, no? So these give different errors, and in the end you want them to be similar, no? So you choose an L, and L is going to be basically choose it to be half the size of it, something like this. It could be a quarter, doesn't matter. Okay, is this clear? So I think this is an interesting statement, because this is telling you, well, that you can approximate local properties of thermal states without diagonalizing the whole system. No? So if you want to study, for instance, like local magnetization of thermal states, some order parameter, whatever, you don't have to diagonalize the whole matrix. No? You can just look at a smaller thermal state, calculate it there, and then you can extrapolate. And this is going to give you a good approximation, which is mathematically guaranteed. Okay. Another reason why I think this is interesting.
Sorry, I have a question concerning how we would split the system usually. So would we always try to split it in 3 parts like this? Because then we would already have the properties of the system that we're interested at. Or if we were in higher dimensions, we would have to concatenate approximations in order to get the properties that we want.
Yes. Right. So here, I guess in this argument that I've done, you care about system A. So you do the partition because according to this, I guess in higher dimensions. So in higher dimensions, all these holes, and I guess you can always do similar partitions, no? So you have
what I meant is that here we are assuming that we only have like Hamiltonians that act on A, B, and B, C. But in practice, we're gonna probably also have one that acts on C, D, and so on.
Yeah. So I guess so. You mean like in 2 dimensions, the boundary is not a single side, no?
Yeah. For example.
Yeah. So in that case, what you have to do is you have to do this argument for each of the terms.
Okay.
So what's gonna happen is that you're gonna have to do this many times. So in the error, you're gonna have a term. You're gonna have a multiplicative factor that feels like the boundary.
Okay, so then if we want to study system A, we would have to do the approximation for all of the different systems that touch A.
Yeah. So so system B. So the boundary between B and C will be many different subsystems, and you have to take.
Okay.
So so you have many of these. You have to take all of them. Maybe you can do it at the same time, kind of, but you can also do it one by one. Yeah.
Okay, thanks.
Yeah. So another reason why I think this proof is interesting is because it's like a relatively simple statement. I think is so. When I was planning this, I was trying to find what is somehow the simplest thing I could prove in 10 minutes like this. But the thing is that this type of argument, with approximating things with local operators or this result by hierarchy, this is basically the way you do. Well, this is in the spirit of most results about like mathematical, anyway, physics or thermal states and so on. So I guess I wanted, this proof to be a bit of an illustration of more complicated things, no? So for instance, this paper by Araki is super old, but it's really important because it's the one where he showed analytically that there's no phase transitions in one dimension. So this similar operator, you can think of this as some sort of transform matrix. No? So then you can, for instance, build your one-dimensional thermal state as a concatenation of this operator. No? And the fact that you can do this perhaps means that your correlation functions decay, no? Because somehow you have a transform matrix that not a transform matrix is an operator, but you're multiplying something many times. So this is how things end up decaying exponentially. No? You have some number that decays with some power. So yeah, so I think this somehow illustrates a particularly powerful technique to study thermal states in one dimension. In higher dimensions, there's other things you can do. There's many other techniques and so on. No, but many others. There's a few, like this cluster expansion that was mentioned before. No, and they really allow you to do like non-trivial statements about really complicated systems. No, and for instance, this type of statement again also allows you to, for instance, prove that you can approximate thermal states in one dimension with tensor networks, because what you end up with is you can approximate your thermal state by a product of smaller operators like this. No, and since you have a product of smaller operators, this is kind of like a tensor network. It's a bit vague for those of you who don't know this, but basically, what the spirit here is that somehow you have these properties that are very non-local on the surface, but then it turns out that you can approximate them locally, no? And this allows you to to understand things in a much more simplified way, no? It's how to diagonalize everything, no? Because basically, when you want to show things, you can do things in sequence, no? So instead of taking exponential time, it takes you polynomial time, no? Because you have to sequence n times, no? Where n is the length of the chain, no? Yeah, so so I derive this in this way, and you can probably do other things with this, even with this just simple. Yeah, I hope that is interesting. So I think with this, I'm more out of time. So, are there any questions?
So we go for a coffee break now, and then we can restart in half an hour. So at 1:15.
No, it wasn't. I'm not sure. I still feel it in my legs.
All right, it's a beautiful day. So let me, as per usual, kind of murder what. So some policies have a large system with local interactions. Everything is thermal, and the question was how well can we approximate kind of an effective local thermal state? And the answer was, exponentially well, depending on how far away is the stuff that we ignore, roughly, right? And now in the second part, we're going to see, well, how the systems get to be thermal in the first place. So,
Yep. Okay, so that's right. That's what I'm going to do in this session. But I guess there's a bit of a twist here. So indeed, I'm going to talk about thermalization. But in the previous lecture, I was talking about the global thermal state. No? So when your whole system is in the deep state, and it might be because it's coupled to some radiation field around it. But now I'm going to talk about a slightly different setting, in which perhaps more surprisingly the thermal or statistical mechanics description appears. And this is basically the setting of quantum quenches. Okay, so now I'm just going to briefly explain this. I guess you can maybe think of it as like a particular experimental setting, and it's kind of interesting. So, okay, so basically I have a system which is a many-body system again, of course, with local interactions as we've seen before, and I start the system in an initial. I can call like this. And because I have to initialize my system in this state, usually this state is going to be something that's relatively simple to prepare. No? So this could be as a product state. So in every site, you use a different value for some property, like spin up or down or something like this. It could also be that you have a simple Hamiltonian and then you pull it down to the ground state. In general, these ground states are also going to be simple states in the sense, for instance, that they also have the kind of decay correlations that thermal states have. No? So yeah, something simple to prepare, nothing too complicated. No? So something you definitely don't need a quantum computer for. Okay, and now the Hamiltonian is quenched, so it's suddenly changed from some h of 0 to some h suddenly, and this is the quench part. So you can think that maybe this state was steady under this Hamiltonian, it was not evolving. Suddenly I change the Hamiltonian, so it starts evolving in time. No? The dynamics. So this is, you just have some standard time evolution, but of course the evolution is unitary. The state is pure, so that your state is going to remain pure forever. No? I mean, when you do this in the experiment, you have errors and so on, but in theory, you is pure. No? And then you measure the state after time evolution. No? And the way you usually measure is, okay, so let's define this as state evolving time. The way you usually measure is through just measuring some simple observables. No? So you're going to measure expectation values of some observables A. And it's this type of thing, this type of quantity that is going to tell you the interesting physics that happen and the interesting physics you're going to see. No? And I would say this is a particular setting, but it's also kind of general. I would say there's two reasons why this is interesting. And one of them is because it's, as you can see, it's somehow simple to prepare in the lab. No, I mean simple. No, so apparently, I don't know this very well, but in cold atom experiments, even ion traps, other things, you can do this type of thing. No, I think there's maybe some cold atoms people in the audience, so maybe they can tell you more about how you do this in practice. Because basically you don't need too much control, no? You just basically it's a unitary evolution that you just turn on and then you leave it be. But however, even if it's a simple setting, somehow there's like a variety of interesting physical things that happen. No? So depending on your Hamiltonian, on your initial conditions, on your observables, you might see different things. No? So for instance, there's a variety of things. No? Maybe let me just quickly list. So one of them that will happen is thermalization. What I'm going to be talking about, of course. But people also, for instance, study things like transport. So about how conserved quantities spread around in evolution. You can also see things like localization, maybe a particular kind of transport. You can see different things happening. No, there's really a huge variety of things. No? People care about this for many reasons. There's also these flow case systems, and where you change the Hamiltonian a little bit. So yeah, I think from the physics perspective, it's an interesting setting, no?
Someone is asking if you change it a bit and then returns to the original, or is this
very good question. After some time, no? Or yeah, so okay, so this is a unitary evolution, and of course there's this Poincaré recurrence theorem or whatever, that after some time the state is going to return to the initial state. However, in many body systems, this recurrence time is huge. I think it can be, in general, it's like exponential in the system size, and it can be like even double exponential in the system size. So in your experiment, you're never going to see the recurrence time. Maybe you see it in like very particular situations that you tune or something like this, but this recurrence time is basically doesn't really matter too much for what you're going to measure. Okay. So hopefully, setting any questions about this? Okay. So now I'm going to talk about what happens in let's say most situations, and I'm not going to define most. The things I'm going to say about this are not really so. In the previous lecture, I actually proved things, and everything I said, you can prove it mathematically. But now, what I'm going to say, most things can pretty much nothing can be proven. No? And if you can prove something, please come talk to me, or just put it in PRL. Okay, so this is basically the phenomenon of equilibration and thermalization. So two things happen, no? So first, equilibration happens. And what is this? So what's going to happen is that you have your observable evolving in time, and what you're going to see is that after some time, this stops evolving in time. So it reaches a steady state, a steady value, no? Which I'm going to call x. So this means that this has equilibrated. No? So usually, if you plot this kind of thing in numerics or whatever, what you see is that you have your t here, you have time, and maybe you start in some value that is far away from equilibrium, you have some evolution, and you start converging to some fixed value, let's say. And there's some small fluctuations around it. If you wait for long enough, it's going to come back to this, but again, this is going to take very long. So the other statement is the thermalization statement. And it's a statement of this quantity. And the statement is that, in general, this equilibration value corresponds to expectation value in a thermal state. So this steady point that you reach here corresponds to a thermal state. The non-trivial thing is also, so this, I guess, well, let's see how I define this. No? And the non-trivial thing is, what is this temperature? Because I mean, this is maybe surprising, no? Because really, this is just a unitary time evolution, no? Your system is always pure, no? The thing is that you're looking at a particular observable, no? Observables that often you can measure in the lab, no? So often, this observable A is going to be a local observable, no? So I guess if I have my chain here, maybe I can measure an operator A that has support on a small piece of a chain, no? So what this is saying is that, as seen by these operators, your global state that is evolving in time is actually not evolving in time. It's not only not evolving in time, is actually saturated to some thermal state. The global state is still pure, of course. And then again, you can maybe, linking to the previous lecture, you could maybe study these expectation values with respect to not the global Hamiltonian, but the local one, or something like this. But this is like an extra thing. What I'm saying here is that this is the global thermal state.
Sorry, did you just say that the state stays pure, but the observable is the value of the thermal
state? Yes. So for instance, if you were to look at some other observable, maybe something super non-local, this will be very different from thermal, because these observables will be able to see that the state is pure. But the point is that somehow these observables are quite difficult to measure in the lab, to measure in the lab, basically. Because typically you can measure things that are local or maybe momentum space or something like this. So this is what happens in most cases. There are exceptions. And each of these exceptions will take its own lecture course, kind of. But let me just mention that, for instance, there's localized systems. So like Anderson or MDL, minimally localized states, maybe you've heard of these terms. There's also exactly solvable model. So for instance, when you think of systems like free fermions and things like this picture does not completely hold. You have to change it a bit. Or like things like you can solve with Bethe ansatz, for those of you who know about this, like Heisenberg models, things like this. And there's also quite a new thing that people are excited about nowadays, which is quantum many-body stars, which are, I don't want to say what this is, but maybe it's good that you hear the name. No? Okay, but I'm not going to talk about any of this. I'm going to talk about the generic cases. These are somehow systems that have particular properties. Okay, so I just want to sort of illustrate the mechanism for why this happens. For this, I'm gonna move here and I'm gonna write things a bit explicitly. So let me define the Hamiltonian in the energy eigenbasis. So I'm gonna label it like this. State. I also can write it in the energy eigenbasis. And the observable. It's just, I'm not doing anything here, no, just. So we can expand let's say, the quantity I care about in this basis. Sum, k, cj, star, k, to the minus t. Is this clear? I'm just writing Schrodinger evolution. There's nothing else here. Okay. So you can see that, there's a lot of information here. No? So this is information about the state. This is information about the observable, and this is information about the Hamiltonian. And there's somehow quite a when you have many numbers here, there's really quite an intricate interplay, no? Between all these things. No? So it's actually quite hard to analyze systematically. No? But somehow there's a picture, like somehow toy picture that maybe tells you why these things happen, and this is what I'm gonna try to describe now. Okay. So I can rewrite this into two terms. Okay. So there's a term that does not depend on time, and there's one that depends on time. So the one that does not depend on time is this. The one that depends on time is the one where, well, I think I'm not being too careful with the degeneracies of the Hamiltonian. So let's assume it's not here. So the reason why I wrote this into terms is because you can now go back to the list of equilibration and thermalization, and each of these terms does one thing. So this one is responsible for the equilibration. This one is responsible for the thermalization. And basically what I want to show is that this one at some point goes to 0, and I want to show that this one converges to thermal value. And actually, sorry, there's something I missed to say. I think I would say now. Just go back to this board. Hello. So there's a non-trivial choice, which is what is the temperature. And the temperature is defined with respect to the initial state, because of course with unitary evolution there's energy conservation. So what's going to happen is that your temperature is chosen such that the following holds. So you have some energy, your initial state has some energy, which is just well defined as this average, and there's going to be a given state with the same energy. No? So this is what tells me what is this temperature. I guess the non-trivial thing is that this defines the beta, and it's the same beta that I find here. That clear? It's not just any beta. No, I cannot choose it. It's fixed.
What does the energy have to do with operator A?
Nothing.
What if the operator A, like for some exotic reason, is also conserved? Can it still?
It doesn't happen. No, there's no time evolution. No, so
okay.
Yeah, because of course, there's no time evolution, so nothing happens.
So, but then the system does not equilibrate. It does not thermalize. I mean,
as seen by this operator, as seen by that operator that you say. Okay. But for others, maybe it does in some sense.
Okay. Yes.
Maybe it thermalizes, but to some ensemble where you have to take into account the extra conservation loss or something like this. No. So here somehow it's a generic setting where there's no really relevant conservation loss. It's the energy conservation.
Okay. Thanks.
Yeah, I come back to this now. Okay, so let's look at this a bit more in detail. First, the first one, thermalization, because I think that's the easiest one to understand. So like I said, I'm just going to repeat. I want this to approximate some thermal value, okay? So this is maybe some of you have heard of ETH. It's not that place. It's the eigenstate thermalization hypothesis. No? So this was first proposed by Srednicki. This was like really some brilliant idea. And I mean, some days I think this is really surprising, and some days I think it's not. So it's really, I don't know. I think this statement is super cool, and that's what I want to explain to you. So basically, what happens in generic system is that these numbers. So J is an eigenstate, no? So it's an energy. No? So its energy corresponds to the energy of some thermal state. No? So what the ETH tells me is that these numbers, there are very many of them, but actually all of them that belong to somehow the same energy window. No? So all of them that have similar energies actually take thermal values. So this means that every eigenstate, when you look at subsystems, when you look at the observables, the expectation value coincides with the thermal. Okay. And there's some corrections, and the corrections are like basically exponentially small. Something like this. So it's basically exponentially small, and the exponent is the entropy of your thermal state. So the entropy grows for thermal state grows linearly with the system size. No? So it's exponentially small in system size.
So I've only heard this in the context of random matrices. So is it somehow like high probability for A or something?
Okay, so this is not rigorous. If you want to make it rigorous, well, actually people don't know how to do this, but not quite. So in real systems, when you look at certain variables that are physically relevant, I'm not going to define what it is because no one knows the exact definition. It's somehow like a bit intuitive or heuristic, if you like. This holds. But the thing is that this is telling you also that somehow your eigenstates of many other systems look a bit like states that you sampled from a random matrix, like eigenstates of a random matrix, actually. So there's some relation with random matrix, yes. But so yeah, somehow eigenstates look kind of like typical eigenstates of a random matrix. But this statement is, I mean, you have to, the random matrix don't capture all the physics, actually. There's a lot more than just that statement, let's say. No? But yeah, but this is a good intuition. No? So actually, this is somehow consistent with what I say, no? That basically, eigenstates of these systems are very chaotic. And how are they chaotic? Because they have shared features with random states, actually. Yeah. So this is actually one way in which people can do exact calculations about these things, no? Using random matrix theory. The problem is that I don't think this gets you all the way, actually. It only captures some features. Random matrix theory is like a simplified toy model of an actual quantum system, I would say.
I'm wondering, the left-hand side, does it somehow depend on the initial state?
Yes, it does, yeah. Good question. Yes, yes. So, okay, so the thing is that the initial state has an energy distribution, which is this. And the point is that I guess I haven't said this in much detail, but it's important now that we chose a state initially that is maybe simple or pure, no? And the reason for this is that these product states, these states with short range correlations, have an energy distribution, and you can prove this actually, have an energy distribution which is very peaked around the average. So this will be like a. So there's some. This is the energy distribution, and this is the average. Actually, the central limit theorem holds for this type of energy distribution. And what happens is that most of these coefficients, or most of the weight, is actually very close to the average energy. So effectively, most of the terms in this average, or the terms with high weight, actually have the same energy. So you don't have in let's say real life situations, you don't have states that have like a bimodal distribution like this, where you will have to take two different thermal states into account. For instance, this doesn't happen in like real life situations. Maybe with some engineering you could take it, but,
And already for the second line, it's the AGG doesn't have the coefficients, so
what I'm saying is that all these numbers average to the thermal state, but the reason for it is that each of those numbers is equal to the average.
And in the second line, the HHJ itself is, because HHJ is just like in the energy eigenbasis, the expectation value, and what does it have to do with the initial state?
The average energy.
Okay.
That's the only thing they have in common. And what I'm saying is that the average energy of the initial state defines your temperature. So it defines the energy window in which your dynamics happen. So the initial state defines which coefficients appear here, and it also defines the temperature.
The question: how do you notice that it has this Gaussian distribution? I mean, shouldn't you choose like an arbitrary initial state?
Yeah, but it's like approximately Gaussian. I guess the point is that your energy is like a local observable, and if your state does not have long range correlations, the energy at each site is like independent. So it's like flipping coins. So it's like you get some central limit theorem type of thing. And your energy, yeah, has like it's approximately Gaussian. It's not exactly Gaussian, but it's like a.
Just an arbitrary state at the beginning, or how do you determine this initial state?
It's arbitrary by, for instance, product. Any product state.
Okay.
Yeah, pretty much. You have to be quite special for this not to hold.
If all of the AJJs kind of they are all the same and the sum is one.
Yeah, so that's exactly what happens here. Yeah. So this is So yeah, exactly. So I guess that was the next thing I was going to say. So yeah. So that this is roughly equal to sum of J squared of J, and yeah, and this is 1 or close to 1. How close it depends on the tails of the distribution, but the tails are small, so it doesn't matter. So yeah, that's how it works. So this is thermalization. And maybe this seems like quite a special property, like it's like all this subsystem, all these numbers and they all should be different, but they're not. No, why does this happen? There's some conspiracy. I guess not. It's how it is, no? Okay.
I have a question. So when does it fail?
It fails, for instance, so in the case where you have conserved quantities, maybe, because in that case, maybe you have to take the different subsectors into account, and for each of these subsectors, you're going to have a different expectation value. It also fails. So, for instance, this maybe this is not super clear, but this implies that your subsystems have are thermal, no? So this means they have there's basically a volume law in entanglement. So the entanglement in your eigenstates is very large, no? So there's systems like this localized system, this MBL, where your entanglement is not very large, it's small in the eigenstates, no? So in that case, for instance, we localize many by localization, this fails completely. So this relies on entanglement in the eigenstates, no? But somehow in many models that are not finely tuned or without solid or whatever generic systems, this holds. It's quite ubiquitous. Now I'm just gonna give a brief picture about the equation part, and this is gonna be even less precise. I spent 2 years trying to prove something along these lines, and I failed. So. I encourage you to try. Okay, so now we look at the other part, which is, I guess, A of P minus the equilibrated value. I guess we already established this thermal. Let me just write this as okay. Just repeating the same question. So this is a mess. So okay, sorry. So this is a bunch of complex numbers that you're adding up. No? So this is very vastly. No? So you can maybe plot this in the complex plane, okay? This is real, this is imaginary. No? So you see that with time, it's a bunch of complex numbers and they're oscillating with different frequencies. And the frequency depends on the energy gap. And somehow the magnitude of the complex number depends on these two things. No? So what's going to happen is that maybe you start with some, in your initial state at time 0, maybe all your points are somehow like aligned, maybe they're real, I don't know, could be. And then they start oscillating with different frequencies. No? So at some point, this cloud of complex numbers, like this mess around the complex plane, okay? And in fact, it's going to be like somehow like a uniform cloud of complex numbers. No? And somehow this happens in such a way that after some time, it goes to 0. And the reason for this is that you have like a uniform distribution of complex numbers, so you add them and they average out to 0. So okay, so let me give some intuition for why this happens. So this happens first of all because these numbers are somehow like quite evenly or randomly distributed. No, it's like really a very messy distribution. No? So somehow it's like in the end it somehow ends up being uniform because it's so complicated. No? So why does this happen? So first of all, there's 3 things. No, there's like the coefficients, the observable, and the gaps, and each of these has a different argument. So for the gaps, what happens in typical Hamiltonians is that your gaps are somehow very non-degenerate, and there's some even distribution. No? So in many systems, maybe some of you have heard of this Wigner-Dyson distribution, which basically means like level repulsion, no? in your spectrum. So all these systems that obey ETH, they obey Wigner-Dyson distribution also. So your gaps are somehow like very different between each other. No, there's not too much regularity among them. No, and for instance, the gaps are also typically non-degenerate. No, because to have maybe degenerate gaps, you need like some symmetry, no? Which we've said doesn't hold. No? And the other thing is the coefficient C of j. And what is this? This is the product between my initial state and some eigenstate. Okay, and we've said that these states are very entangled, and this state is not, because this has somehow short-range correlations. No? So it could be a product state. So the overlap between a very entangled state and a product state is very small. So what's going to happen is that each of these numbers is actually exponentially small. So you have an exponential amount of these numbers because you have an exponential amount of eigenstates in the spectrum, even in like a particular energy window, and each of them has like small magnitude. No, so it's like there's very many of them, and they're all very small. No? And the last thing, perhaps the most interesting, is the observable. And again, this has to do with the ETH. So what I said there is the diagonal part of ETH because it cares about A of JJ, which is the diagonal of the observable in the energy eigenbasis. But the off diagonal is the one that talks about dynamics. No? So there's also an ansatz for this. And the ansatz is the following. I mean, this is it's quite something. Ansatz. Okay, there's a lot to unpack here, but maybe let me summarize. So there's a few things. First of all, what this is telling me is that each of these numbers, there's very many of them. I mean, how many? Exponentially many, no? There's as many as this, no? As many as there are eigenstates in our dynamics, no? So each of them is small, exponentially small. No? So they're also kind of evenly distributed, but they're not completely evenly distributed because there's a factor here that actually has some. This is a function that depends on the average energy. So this is the energy of my initial state. No, this E is the energy of my initial state. And this is the frequency of the particular term in the matrix. And somehow this dependence on both the energy and the frequency. So this tells you something about time scales actually. No, so the way this function decays maybe tells you something about how the energy distribution of these things. No? So for instance, people associate this function with the linear response theorems and dissipation theorems, things like this. And then there's this other thing, which is the thermodynamics. It's just random numbers between 0 and 1. So this is a mess, right? But and the thing is that this is an ansatz, and it's actually not true. It doesn't tell you the whole thing. But the thing you should just notice here is that it's telling you that all these numbers are very evenly distributed. So all these things together end up, they end up causing that this cloud of complex numbers averages to 0. Yeah, and this is kind of like a not very rigorous picture, no? And I think making this rigorous is like a real challenge. No, it's super difficult because you have to know a lot of things about the structure of these things. No? But intuitively, you can more or less see what happens. No, and if you do numerics, you see this very well. No, there's some proposals about the time scale of these things, but it's hard to make a general statement. No, because this is, all the things are very general. No, of course, there's many different observables with different fine-grained features and so on. No? So. It's hard, for instance, a question that is really hard is to know how long it takes for this to approximate 0. How long it takes is going to be related to the energy gaps, for instance. So the frequencies that oscillate. Yeah, so people have been trying to, find some bounds on the time scale, things like this. Okay, so I have 10 minutes now, more or less. Okay, so actually, in the last 10 minutes, I will go back to the mathematical argument. I don't want to have a lecture without a proof, basically. So I'm going to do a proof of something that can be, that can be shown. Any questions about this before I move on? So what I'm going to talk about is now something that I guess I'm going to call lifetime around equilibrium. Enough time. Let's see. So this is a result. I think it appeared so simultaneously by Riemann. There's also another paper from the groups of from Bristol. The first author is Tony Short. 2008. I'm gonna follow this proof, but they're basically the same thing. Okay. So what I want to show now is that basically so we established two things. We established that at some point in time your observables look thermal, and that somehow it takes not too long to reach that steady state value. No? So I want to bound the fluctuations around this steady state value. No? For late times. How late? Very late. Okay, so let's see. So I'm going to start with the definition. The definition is the diagonal ensemble. So this is defined as follows. It's defined in terms of initial state that I talked about earlier. So I'm going to follow the same notation. So this is a state that is steady, is diagonal in the energy gain basis. It's not thermal because this distribution is not thermal, but we know that it looks thermal, no? Because if I take the expectation value of this state with respect to A, I get the quantity that ETH was telling me that it looks thermal. No? Okay, but let's say, I mean, we don't care about this part now. We don't care that whether it looks thermal or not. We just care that this is the case. So I'm going to compare the two following numbers. T minus the expectation value of A in the diagonal ensemble. Okay. So this is basically the difference between the thing that is actually evolving in time and a steady value. No? And the point is that somehow, if this converges to some value, it's going to converge to this value. No? When it stops evolving in time. No? So yeah, at some point when this thing stops evolving in time, this whole thing is going to be approximately zero. So okay, so maybe I just take the square. And I'm going to average over time. So what's happening here is that I'm looking at time from 0 to t. I'm going to be tight on time. Let's see. So I'm going to average in terms of 0 and t. And as I said, the plot of this thing is maybe something like this. And at some point, we reach a steady state. And there's like very small fluctuations around it. No? So I want to bound these fluctuations. No? So for very late times, so imagine I take a time that is very far from here. The contribution to the average from this part is small, and the big contribution should come from the very small fluctuations, which are small, but they happen for a very long time. No? So maybe they add up. And in fact, the only way in which I can do a calculation is by taking the limit of t goes to infinity. And I want to put an upper bound on this quantity. Okay. And what this is going to tell me is basically the size of these fluctuations around the value that is the equilibrium value, no? whichever it is. Notice that because I'm taking the limit of t goes to infinity, I'm not saying anything about the time scales, no? About how long it takes to reach this steady state value. But at least you can say something. No? It's still a non-trivial statement, I would say. In particular, because maybe for different models, this kind of quantity will behave differently. To keep this. Okay, maybe let's move back here and I just now be ready because now this is where the proof begins. Right. I have 5 minutes. Okay, so I'm going to expand this expression in the energy gain basis. Okay, so let me write. The camera. The energy gain basis, this looks like the following. It's a bit complicated, but it will simplify in a second. 4 frequencies, 4 energies actually. CL, C, A, C, M, C, L. So I have now 4 different indices, J, K, L, M. Each of these is a label for an energy. Okay. A, J, K, A, L, M. And you see this thing appears twice because I've taken the square over there, and the state also appears squared, no? So I have a bit more of a complicated expression. And then I have limit t goes to infinity of the quantity that evolves in time. Okay. Sorry. And the quantity variables in time is just an exponential. Minus. And now the non-trivial part is that we want to simplify this. No? So with this integral you can just do, okay? And it's and basically, well, if you do it a bit carefully, what you can see is that it's somehow like a delta function. So if this is 0, this whole thing is 1, and yeah, and otherwise is 0. No? So actually, maybe I shouldn't in full, but essentially this is somehow delta function of this one assumption I want to make. It's important. It's the assumption of non-degenerate energy gaps. Okay. So what this means, and this is typically, this seems a bit weird, but actually typically holds in systems, at least approximately. So what this means is that if two energy gaps are equal, it's because this energy is the same as this energy, and this is the same as this. So let me just simplify it. J equals L, K equals M. So this is an assumption. This is an assumption that I'm putting into the proof, but you know it should be a good approximation of what happens. So from this assumption, what we get is that this whole thing ends up being a delta function. Well, two delta functions actually. L delta. Okay. So this whole thing simplifies quite a bit. But it simplifies to this. It's not equal to M, and this is not equal is because actually I've taken out. So sorry, you say here J is not equal to K. Here L is not equal to M because we already subtracted the diagonal ensemble. Sorry, this is a bit too fast. But hopefully you're getting the idea. J squared A squared A J K. Okay, so actually now everything is positive. We will get rid of the complex numbers. It's a bit easier to analyze. So we can do an upper bound. And the upper bound is pretty trivial. I just add terms. So now I sum over all J and M. Oh, it should be M. It's to be consistent. And this turns out to be equal to the following thing. Trace of the row with this is the diagonal ensemble from there. The dagger row. Okay, so now I'm gonna, it's just a couple more steps. Sorry, can I go a couple of minutes more time?
I mean, you should be ending now, but can you give 5 minutes? Fine.
Yeah, no, it's just no, 5 is, yeah, I have plenty with 5 years. Okay, so the last thing I wrote is this, and this is what I want to upper bound. So you can use this thing called the Cauchy-Schwarz inequality, which basically tells me that the following trace of x, y is a square is smaller than trace of x bar, trace of y, y1. Anyway, so you do this and you get the following: the square root. You apply this here. Dagger, row squared, and then this trace. Trace. And dagger, row squared again. And then you can use this Euler's inequality from the previous lecture. And what you end up with is the following: is the and this basically the answer. Of A squared times the 1 norm.
Sorry, just a question. The trace, the second trace in the square root, is it?
It's, oh, sorry, no, this is wrong. Yeah, sorry, this is so this is okay. So one of them is dagger, not dagger, and the other one is the opposite.
Okay.
Right. So actually, if A is Hermitian, which probably I should have said, or I could have assumed, they're the same. So you get this, and this is actually equal to the trace because this is positive. So you end up with trace of rho squared. This is basically the purity of this ensemble. No? So this number is very small because, as I said, this distribution is like a Gaussian, right? And somehow this is somehow the well, for a Gaussian this number is very small, no? Because this number is basically very small if I have very many terms in my distribution. No? This is the purity. No? So if my distribution is very evenly spread, this number should be very small. No? Is that clear? Okay. So in particular, you can show in quite some general settings that this is actually for most systems and for many initial states and for, I mean, this also depends on the spectrum, no? Because you have to make this assumption. This is initially small. No? So what we've shown here in quite simple terms is basically that the fluctuations around the equilibrium value, when you average over all times, no, they decay exponentially with system size. So they really become suppressed, no? And I think the main question that this leaves open is this limit of t goes to infinity, no? It would be really nice to do a similar calculation where t does not go to infinity. And then you can maybe see some time scale in this decay, no? But this is difficult because of course many of this, I mean, it just doesn't go through at all. No? And yeah, hopefully this somehow also supports what I said before, no? That all these numbers average out to 0, no? Because they are very spread, no? And somehow this is telling you something along those lines, no? What is telling you to be weaker because we're making it formal, no? But you see that at least. No? And yeah, I guess with this I can finish. Are there any questions?
Let's thank Albert.